It's 2 o'clock. Ooh, this mic is working. This whole lapel situation, we weren't sure. So welcome back to day 2. Show of hands, who got more than 6 hours of sleep last night? Pretty typical. Excellent. Okay, good. Part of the fun of Combustion Summer School is hanging out with people. So I was talking to Dr. Chen this morning, and we're glad that we're teaching the first half of the week. So you're alert and ready to go. Okay, so we're going to continue, pick up right where we left off from last time. So just a quick review of key points. I hate slides that are filled with text, but here's a slide that's filled with text. And this is just the high-level overview of what we talked about yesterday. So thermoacoustic instability is driven by a feedback process between pressure and heat release. And what we really talked about, and hopefully the message that you took home from that discussion, was that the phase between these two oscillations is really what drives the instability. You can have an acoustic mode, but unless the heat release rate oscillations are lined up properly with that acoustic mode in both space and time, you won't get instability. The other piece of it is that you need that thermoacoustic driving to be greater than the damping in the system. And I got some really good questions after class yesterday on damping. And we're going to talk more about that today when we talk about instability control. The second piece is this final amplitude, or what we call the limit cycle amplitude, is determined by the level of nonlinearity in the flame response. And one of the things that we talked about last time was the fundamental place that this nonlinearity comes from. Using our craft here, we looked at flame wrinkles of different wavelengths and what's called, the word that's used in the literature is kinematic restoration. And so if you have a wrinkle in the flame, as it propagates into itself and it becomes not wrinkled anymore, that restoration of the flat flame and that very nonlinear destruction of flame area is referred to as kinematic restoration. And it is the fundamental source of nonlinearity in flame response. So if we have very weak driving of the system, you'll get very low amplitude wrinkles, and you'll get a pretty linear response as those propagate along the flame. But you get these big wrinkles with high curvatures, you get very nonlinear flame area collapse as a result of that shape. There are other sources of nonlinearity in flame response, and I'd be happy to talk about those at the end of class if folks have questions. But this is the fundamental one, and really the one I want you to take home. And so I'm going to skip to the last point here. One of the impacts of this is that flames act as low-pass filters, right? So if we put really small wrinkles on the flame, these end up cusping and forming cusping and destroying themselves very quickly. And so the resultant flame area oscillation, and as a result, the resultant heat release rate oscillation is very low because you have very quick destruction. And at some point, the flame just doesn't respond anymore. And we'll see a ton of both theory and data about that today. The final thing that we talked about were coupling mechanisms, that you had these different disturbances that could drive fluctuations on the flame, that the acoustic oscillations drove some sort of other oscillation, and it was this other coupling oscillation that drove the flame response. And in particular, we focused on velocity coupling yesterday, because that's the easiest thing to do with pipe cleaners. But you could use the same theory that we presented to look at equivalence ratio fluctuations, pressure fluctuations, a whole bunch of different things. And I provided a reference from Sébastien Ducrix and his colleagues at École Centrale about that. So those were the main themes that we talked about yesterday. And so today we're going to build off that. The first thing we're going to talk about, yesterday we talked about local flame response or flame kinematics. But what we really care about in this thermoacoustic feedback loop is the global flame response, right? What's the total heat release rate doing? And then how does that couple with the thermoacoustic feedback process? And that's really what we're going to focus on first. The way that we quantify this is using something called flame transfer functions. So we're going to have a quick intro to control theory for folks who have forgotten their transfer functions, which is okay. And we'll look at a ton of data that ties together things that we've learned about basic flame kinematics and these flame transfer functions. And one of my main goals, because flame transfer functions are a really common way of talking about flame response, I want you to be able to look at a flame transfer function and infer the flame kinematics from it, which we'll talk about. Again, the brakes are all in the wrong place, so ignore that. The last big topic we're going to talk about is instability control. And there are a bunch of different control mechanisms that we use in real systems to damp these instabilities. We'll talk about a bonus control method, which is some of the research that I'm doing that has to do with hydrodynamic response. And if anybody saw my plenary at the symposium 2 years ago, this is going to be a bit of a review of that. But if they didn't, this will be new and kind of fun. And then there are some advanced topics. But just a quick reminder, I've purposefully left time at the end to address topics that folks are interested in. So, you know, be ready to talk about stuff at the end. And hopefully we will not have melted in this room that does not have air conditioning. Okay, so that's what we're doing today. Any questions before we get going? No? Okay, cool. All right, so we're going to talk about flame response. And the framework that we use to discuss this is called a flame transfer function. One of the things I have found through my career is that control theorists have all the math you need to do the work, particularly in dynamical systems, but they don't always have the disciplinary knowledge in order to apply it. And so I have in the past worked really closely with control theorists and realized that a lot of what we do, or things that I thought were very innovative, are things that control theorists do all the time. You know, if you're going into this field, I would recommend not only some courses in nonlinear dynamics, which we talked about yesterday, and there's actually a great YouTube series. If anybody wants to watch that, I can talk about that later. But also courses in control theory, because that's where a lot of this math comes from. Okay, so the basic structure of a transfer function, not just a flame transfer function, just a transfer function in general, is that you have some input. We had some input. Oh, because it's not on. Way to go, Connor. All right. You have some input, and in this case, it's an input velocity fluctuation typically, or it could be equivalence ratio fluctuation or pressure fluctuation, depends on what your coupling mechanism is, but in this, today we're going to talk about velocity fluctuations. And what comes out of the system, where the system is, you know, the flame, what comes out of the system is the output heat release rate fluctuation. And the transfer function is the function that describes this input-output relationship. This is called a CESO system, a single input, single output system. There are multiple input, single output, multiple input, multiple output. There are a whole bunch of acronyms that go with this. This is a very common linear concept that describes the responsive systems. And so so now at this point I did just put some math in the slides. So if you have the slides, you're going to see all this. So this is what we had been talking about yesterday. We said I have some input velocity field and it has a mean and a fluctuation. And I don't want to work in omega, so I'm going to throw in a 2 pi f, right? Like we said before, I don't want to do any of this in the time domain because I don't remember any of this jazz. And so we're going to do the Fourier transform. And when you do the Fourier transform, you end up with some input velocity fluctuation as a function of frequency. And we'll talk about in just a sec how we measure these. You can see that our transfer function G is a function of frequency. It's a frequency domain concept, which is true here and in control theory more generally. All right, so that's the input. You can play the same game on the output, right? So now I have some heat release response. I have a total heat release, which is the time average plus the fluctuation. And I go forth and do my Fourier transform, and now I have some Q hat of F. So that's at each frequency, the amplitude and phase of the heat release rate response. And then to define my flame transfer function, I just take a ratio. And so here it's a normalized ratio so that the transfer function doesn't have a unit, because I don't know what the units of heat release rate over velocity are. And I'd like to be able to compare this between different systems. And so what we do is we take the response as a function of frequency, normalize it by the time average, the input as a function of frequency, normalized by its time average, and then you get this transfer function. Kind of make sense? Okay, cool. Remember that Fourier transforms are complex numbers. And so what ends up happening is this transfer function has two components. One is the gain of the transfer function, and one is the phase of the transfer function. And so the gain is just the absolute value of this quantity, and the phase is the inverse tangent, or the phase. If you're using MATLAB or something, you use either the phase or angle command. Okay, so this is how we define it, and so we get a gain and a phase. The way that we typically plot transfer functions are called Bode diagrams. And I'm going to tell you a somewhat embarrassing but important story about paying attention in class. When I was in undergrad, I was totally convinced. I knew I was going to go into combustion. I was like hardcore fluid mechanics. I was going to do gas turbines or bust. And I'm in this controls class, and by the end of the class, the last two things we learned about were Nyquist diagrams, which, full disclosure, I still don't super understand. Sometimes I get a little wrapped around a pole. And then Bode diagrams. And I just gave up. I was like, I'm never going to use this again. 21-year-old Jackie really knew what was going on. And then I get to grad school, and I realize everything I do is a Bode diagram. And I greatly regretted not paying attention in that course. So the moral of that story is take courses and pay attention to them, because they're going to come and bite you in the butt later. All right, but Stack Exchange has a really nice set of pictures, which is what I borrowed for this, that basically describe what a transfer function is. And so yesterday we talked about resonances. You don't just have resonances in acoustic systems. You have resonances in any oscillatory system. You can think about a spring mass damper system that has a preferred frequency or a resonance frequency. And so this is a really standard resonant or dynamic system, and with a damping term in it. And so you have some resonance. And you can see the way that we're plotting up here is just the amplitude or the gain of the transfer function. We're plotting as a function of frequency what the amplitude is. And so you can see the peak amplitude is at this resonant frequency. And the amplitude's going to change based on what your damping is. So this zeta term right here is your damping. So if you lower the damping, the peak gets higher. If you have a system with no damping, which you can do in theory, but you can't do in practice, you have a peak with an infinite amplitude at the resonant frequency. And so similarly, down here is just a plot of a bunch of different transfer functions. As you go up in color here, the damping is going down. So this is the amplitude. Now this is on log scale, which is often how we look at these things. This is the phase. And so, like we saw before, we have a gain and a phase. What the phase tells you, so the gain tells you the ratio of these two things. So if the gain is greater than 1, that means if I put a unit input, what comes out the back end is greater than 1. If I have a gain less than 1, if I put in a unit input, what comes out the back end is less than 1. And this is another reason that normalizing this is really nice. But the phase tells you the phase between these two oscillations. And so that's really useful right? If I need to know what the phase is for a thermoacoustic feedback cycle, this is a way to measure or calculate it if you're calculating your transfer function. And so here, at every different frequency, you can see the phase between these two disturbances. Okay, so this was, what it looks like on just for a general circuit system, right? Not too exciting, but let's now look at what this looks like for flames. Before we start looking at a bunch of examples of transfer functions, I want to quickly just talk about how we use them. They're particularly useful for figuring out whether your system's going to be unstable or not. Because the transfer function is a linear concept, it by definition cannot tell you what the limit cycle amplitude is. Let me say that one more time. Because the flame transfer function is a linear concept, it cannot tell you what the limit cycle amplitude or the final amplitude of the instability is. This is super important. What it can tell you, though, because it tells you if there's amplification, right, if the gain's greater than 1, or non-amplification, and it tells you the phase between these two disturbances that are super important in the feedback cycle, it can help tell you if the system has, if thermoacoustic driving is positive for your particular system. So the way that we typically use these is we either calculate or we measure the flame transfer function, and we're going to talk about how to do both of those things over the next hour. And then you pair it with knowledge of the acoustic field. So this is a simulation. If you remember from the very beginning of yesterday, I had done some work on a package boiler system at a paper mill, and this was an acoustic simulation of that package boiler system. This took forever to set up, but then it took like minutes to run, because solving the wave equation, or in frequency space, the wave equation is called the Helmholtz equation. Solving the Helmholtz equation is super fast. And so what you can do is, if you have an acoustic solver like this plus a flame transfer function, what you end up with is information about what acoustic modes could couple with the flame. And if those acoustic modes are close to resonant frequencies of the flame, where you get these peaks in the response, then you could have some problems, right? So this is able to tell you if your system, in the absence of damping, could be thermoacoustically unstable or not. And that's super helpful, right? And so that's why people have spent a lot of time measuring these and calculating these, and then kludging them together with pretty easy acoustic solvers, because they give you a warning signal, like warning, at this operating condition, you could have an instability if the system's not damped enough. That make sense? All right, so they're super useful. Basically, every major gas turbine manufacturer has some thermoacoustic modeling program. They're all built in-house. There's no software you can go out and buy, where they stick in a flame transfer function, either a measured one or a calculated one. They have very nice acoustic solvers, and they tell you, is this, over different operating ranges for different engine configurations, where are we going to get instabilities? Where are those islands in the operating map that could be unstable? And that's very, very helpful before you go do an engine test and find an instability on the fly, which can be kind of dangerous. Okay. So this is why we want to know. All right, so first we're going to talk about how we measure them. And to do this, we're going to use an example from the lab that I inherited. So this is an experiment that was built by a guy named Nick Bunce. He was one of Dom Santovica's students. Nick and I kind of did our PhDs at the same time, except Nick was at Penn State and I was at Georgia Tech, but our groups worked really closely, so I was very familiar with this. And I'll show you later on, Nick did an experiment that I thought was extraordinarily clever, but then it only got published in his thesis. It never got published in a paper, and it makes me sad because it was a very good piece of work. So you're going to see it today. Okay, so this experiment, basically we have some sort of fuel injector here, and then a combustor, and then an exhaust section. And this is a back pressure valve and that kind of stuff, right? So you could pressurize the system. Upstream of the injector nozzle is a siren. And so in this system, the air comes in here and gets split. There are these two gate valves that control the split between the main pass and the siren pass. Inside, you can see this thing has like a belt that's turning. In real life, we put a cage over it so you can't like get your hair stuck in there or something. But basically, inside this siren, there's a stationary plate with a bunch of holes in it, and then there's a rotating plate with one hole in it. And so as the holes line up, you let air through in a periodic fashion. And so if you've ever seen like an old surfer film or something where, you know, the shark's coming in and some guy is like cranking a siren and it has this like, you know, wail to it, that's what this is. We don't make great grad students crank it. We have a motor that does it for us. And you can turn this thing and get forcing frequencies between about 80 hertz and 500 hertz. So that's 80 fluctuations per second to 500 fluctuations per second, which are frequencies that are important for gas turbines, which is the application for this device. So what we do is we operate the combustor at a stable operating point. So there's no self-excited instability. The flame's nice and quiet. And then we input a frequency, right? So we tune these gate valves so that we get some small amplitude, typically like the standard across measurements is 5%. So your U prime over U bar is 5%, which is a small number, so you get the linear response. And you do this at a whole bunch of different frequencies so that you get the frequency response of the flame. Based on the transfer function, you need to be able to measure the acoustic velocity fluctuation, and we do that with something called a multi-microphone method. So you can see in this injector, these are the swirler vanes here, there's a center body, and then the fuel is injected on the swirler vanes, or it's perfectly premixed upstream. And for these studies, it was perfectly premixed, and we can get into why later if you're curious. So you have a perfectly premixed mixture of fuel and air. It's being forced by the siren, where U prime over U bar is 5%. And then just ahead of where the flame attaches at the end of the center body, we measure two pressures, two acoustic pressures. These are piezoelectric pressure transducers in water cooling jackets, because it gets pretty hot here. We can use those two pressures to calculate the acoustic velocity fluctuation. So a quick review of our acoustics yesterday. This is one of the reasons that I went through and looked at this solution. So what I'm going to show is called the 2-microphone method, but you can do this with any number of microphones, and your accuracy goes up as you have more microphones. But let's assume we have a constant area duct with some acoustic mode in it, and I'm measuring two pressures, P1 and P2, at two distances, you know, 0 and L. Doesn't matter where you put the reference point. Like we talked about yesterday, the solution to this plane wave propagation through this duct looks like this. So we're assuming that we only have propagation in this direction. This breaks down if you have an acoustic mode in a transverse direction. But in a duct, I mean, the duct is this thin and this long, right? So you're really only going to have that longitudinal mode. And so the solution looks like this, right? We saw this before. It's the real part of the forward traveling wave and the backward traveling wave, all multiplied by your fluctuation in time. So then I told you I don't like working in the time domain. Plus, I'm forcing this at individual frequencies. We go through, and every 10 or 20 hertz, we force it, make a measurement, force it, make a measurement. Right, so there's no sense in doing this in the time domain. We're going to do this all in the frequency domain. So I can take the Fourier transform of my two pressures here, and now I have a solution that looks like this. So I have two measurements, and I have two unknowns. I know what K is. because I know what frequency I'm forcing at, and I can calculate the speed of sound, right? K is omega over C, so that's cool. And so now I just need to do some math to turn P1 and P2 into P plus and P minus. And so I know I put in my x locations into each of these equations. So P1 is P plus plus P minus. P2 is that with some phase offset because of that distance. And then, that's a linear. You can math that, and you end up with an equation. You basically get P plus and P minus. Then I got to turn this into a velocity, and I can do that using momentum conservation. So this is the momentum conservation equation in the frequency domain. Assuming no viscous losses and no mean flow effects, the places where this works is there's basically no viscous losses and acoustic fluctuations until you get to insanely high amplitudes. But we're at 5%, right? So we're not going to have that. And the mean flow, basically, if the Mach number's low, it's fine. So the mean flow velocity through this channel is like 40 meters per second. And the speed of sound at the temperature we preheat it to is almost 500 meters per second. So we're solidly in a low Mach number regime. And so basically, you can use the P plus and P minus you get to get a velocity fluctuation at any location along here, which is very useful. So this is how we get our velocity fluctuation. How do we get the heat release rate fluctuation? So there's no device that measures heat release rate directly. If somebody wants to invent one, come talk to me at the break. You and I will patent it, and then we'll become very rich together. But what we do instead is we use chemiluminescence as the stand-in. So chemiluminescence is the light that is emitted during chemical reactions from electronically excited species. This is a series of images from another one of Dom's students, a guy named Steve Peluso. And these are just phase-resolved chemiluminescence images of the flame as it's being acoustically forced. So you can kind of see it goes through this oscillation pattern. And then what he did, you don't need to image it. You could just use the photomultiplier tube. So basically, this is just a little device. They're a few $100. It turns photons into electrons. It's got an amplifier in there. And so if you filter it at the right wavelength, you can get global chemiluminescence measurements at a pretty high repetition rate. Usually we're taking this data at like 20 kilohertz, so we get really nice time resolution of both the pressure and the chemiluminescence. But one of the things that Steve wanted to see was, do the images line up with what we're measuring in the PMT? And they do. And so the dotted line is the super high resolution global chemiluminescence measurements. The squares here are chemiluminescence filtered at 430 nanometers, which is CH star. And then the dots are just like the total signal. And everything's going in concert, right? So this is good. So you basically measure, you estimate your Q prime over Q bar from this PMT. And because you have this data at such a high repetition rate, you can very confidently, with high frequency resolution, do a fast Fourier transform and get your frequency domain response. We have pressure data at 20 kilohertz, and we can turn that into acoustic velocity fluctuation, and then you can build your transfer function from that. And so this is what it looks like. So this is going back to Nick's thesis, and I'll walk through what each of these images are. So on the left is the gain of the transfer function. You can see the first frequency he looked at was 100 hertz. The motor gets a little burnt out if you run at 80 for too long. And so, and if you look at his thesis, he did a lot of these measurements. So he started most of them at 100. But every 20 hertz, he goes through and he reruns the experiment. The PMT systems we have actually have 3 PMTs with 3 different filters, a CH star, an OH star, and a CO2 star. And so this just shows the signal from all 3 of them, which line up really closely, which is good. As a function of frequency, you can see initially if this line here is a gain of 1, initially you start with a gain greater than 1, so an amplification. You get a node. It goes back up, you get a node, and then it goes back up. And this is a very typical flame response for these types of flames. And we will talk about why in just a second. So this is the gain of the transfer function. This is the phase of the transfer function. And this is what's called a wrapped phase. So he's going from negative 180 to 180. I prefer to look at phases wrapped, or unwrapped instead of wrapped, but whatever, it doesn't really matter. Just imagine, you can see as it repeats, you could just imagine it continuing to go down. And then this final thing is the coherence between the chemiluminescence signal and the acoustic signal. And you can see the coherence is between 99% and 100% the entire time. So this is signaling a very strong flame response. You can turn this coherence into an uncertainty for the transfer functions, which is what he's done here. And there are really standard ways to do this. If you want to learn more about transfer functions, there's a really good book called Random Data by Bendat and Pearsall. It's sort of like the Bible of data processing. My copy is very beat up after doing a lot of this in grad school and then handing it to a lot of my grad students when I was a professor. But the details of a lot of the theory for this, or at least this type of data processing, is in there. But today, I really want to focus on the physical meaning, because it's kind of interesting that they have these shapes. So we're not going to talk too much about the phase. We could talk more about it later if you want. But let's just focus on the gain here for a second. So this is just the picture you saw before, and I'm going to highlight a couple things. I've put a dotted line across where the gain equals 1, so you can see where there's amplification. So the first is that at low frequencies, the flame acts as an amplifier. And then, granted, non-monotonically, the gain decreases as the frequency increases. And why is that? Because flames act as low-pass filters. So this is your first, it's a weird filter, right? But the gain goes down as you get to higher frequencies. And if the siren wasn't going to explode past 440 hertz, you'd see that continue to go down. Okay, cool. One thing that's not shown here, because the siren would burn out, you can show from theory for any transfer function, the gain at a frequency of 0 should equal 1. And that's just math. And there are some measurements, people who do these differently, where you can do very low frequency forcing. You can see their measurements get to 1 at a frequency of like close to 0. So that's good. That checks out. But the super interesting part of this shape are these two nodes. And these two nodes suggest the presence of a cancellation phenomenon. And so this is why we spent so much time with pipe cleaners yesterday, is because what we're going to do is we're going to work through the flame kinematics and show what's canceling, because everything we talked about yesterday describes why these things look the way they do. Okay, so one of the nice things about Nick's thesis, which is you can get every Penn State thesis for free online, is that he did a ton of different variations. There was a period at the early 2000s where it was very in vogue to measure flame transfer functions. You'd go to Turbo Expo, which is where most of the instability work for the gas turbine community is presented. And it's just like flame transfer function paper after flame transfer function paper after flame transfer function paper. There are a lot of flame transfer functions. And so we spent a lot of time trying to understand what's going on. So the first variation was a variation in velocity. And so you can see as we go from blue to purple, or magenta, I don't know, we're increasing velocity from 20 meters per second to 30 meters per second. It's not a huge increase in velocity, but 50%, not so bad. And what you can see is that the node, the place where the minimum occurs, moves to a higher frequency. Right? So for the blue signal, the minimum is over here, right? So this one comes down and then goes back up. That's the lowest velocity. For this one, the purple comes down and then goes back up. So there's a 50 hertz difference between these two minima. Does this make sense? Similarly, you can look at this in the phase. The phase between the two oscillations is bigger, it's more negative, for the slow-moving velocity than it is for the fast-moving velocity. Why would this be?
Is it because the round trip time of a wave increases as you superpose the velocity?
So it's not the round trip time, it's another trip time though. So if we have some disturbance that's convecting, what velocity is it going to be convecting at? Yeah, free stream velocity-ish, right? And so if you increase the free stream velocity, that velocity disturbance, that coupling velocity disturbance, will be convecting faster. And so both the phase between your two oscillations will get shorter, right? Lower phase is shorter in time. And the frequency at which these phenomena cancel, this one you'll understand a little bit more as we get further in, goes to a higher frequency, right? And so here, this is where phase is super important, because now we have a difference between, the phase difference between the input perturbation and the output heat release rate oscillation is really what matters. And if your input perturbation is just moving faster, that phase is going to get shorter or smaller, and that time delay or phase lag is going to get shorter. Does that make sense? Let's play this game again. Equivalence ratio. So he went from 0.6 to 0.75. So 0.6 is the blue, 0.75 is the black. And again, if you look at the phase differences, which is this bit messy, but the phase differences here, you can see that the 0.6 has the largest phase difference and the 0.75 has the smallest phase difference. Why do we think that is?
Velocity increases.
Huh?
S sub u, the burning velocity increases.
Yes, so the burning velocity increases, so what happens to the flame length? It shortens. So now your source of heat release rate fluctuation, or the flame center basically, is closer to your disturbance. And so the phase lag gets shorter. Yeah? One more game. Preheat temperature. So can go from 373 Kelvin to 473 Kelvin. The nodes move to higher frequency as the temperature increases, and the phase difference decreases with increasing temperature. What's happening here? As we increase the temperature, what happens to the flame?
Speed of sound increases.
Speed of sound is interesting. It's a second order effect.
Okay, so your burning velocity increases.
Right, your flame speed gets faster, so your flame gets shorter, and now your delay time is shorter as well. So all these remember one of the main messages yesterday was phase lag is all that matters. And now you can see this showing up really nicely in our measurement of phase lag, which is the phase of the transfer function. But then also, very importantly, the shape of the gain response in frequency space. And that's super important because, okay, that thing's going to die, so I'll just keep using this. If I have a system whose, let's go to this one so we don't have any speed of sound problems. If I have a system whose resonant frequency is 250 hertz, then running the velocity faster means that I have a lower gain than if I run the velocity slower. The resonant frequencies of the system kind of are what they are, right, at a given temperature, so given speed of sound. And so how I change that flame shape and how I change these delay times are going to determine how much the flame responds. And so these changes have like could have really big implications for whether or not I have thermoacoustic feedback or not. And you can understand these using kinematics. Okay, cool. Any questions on this before we go forward? It's a lot of data all at once. But one of the reasons I really like his thesis is just like super clear. And he did all these perturbations, and so we can really tease things out. Okay. So there was like a series of DOM students, and in their thesis, they all have this plot, which is every data point they ever took on one graph. I love it. And you can like kind of see, so let's look at the gain plot. You can kind of see the shape, but like, where's the minimum? I don't know. What's going on? I don't know. The phase, holy crap. And so one of the things, part of the problem is that here you're varying velocity and equivalence ratio and preheat temperature and all this other stuff. And having a dimensional quantity on the x-axis isn't a great way of looking at that. So one of the things we often do, like good little fluid mechanicists, is we non-dimensionalize the frequency into what's called the Struhal number. And so to do that, you multiply the frequency times the flame length, divide it by the mean flow velocity. And when you replot all of these versus Struhal number, it looks a lot better. It's not 100%, right? There's still some scatter. And in a plot like this, if you put all the uncertainty bars in there, it'd be an absolute nightmare. But it does collapse things pretty well. And so that works out pretty nicely. I hesitate using the word collapse. I was in a seminar once with a colleague of mine who really grilled the seminar speaker about their meaning of the word collapse. And I think he would say that this data hasn't collapsed. But it has certainly gotten better, right, through this non-dimensionalization. Okay, so this is what actual data looks like, right? This is on an atmospheric rig, but if you look, people have done this in pressurized studies. This is industrial hardware. So, you know, this is what real flame response looks like. So the next question is, what's up with this cancellation phenomenon? Why do we see these nodes and antinodes in the frequency response? And the answer goes back to the theory that we talked about yesterday. So now we're going to go back to our pipe cleaners. Everybody get your crafts out. And we're going to go back and we're going to talk about level set formulations. Okay, the paper that this is from, again, is one of the best starter references on this. This was work that was done by two of my favorite academic siblings, Princeton and Santosham Chandra, when I was pretty new in the group. But it does a really nice job explaining what's going on. So all the theory in the paper, again, we saw this yesterday, they did for both a cone flame and a wedge flame. We're only going to look at wedge flame results because that's what we have pipe cleaners for. And before we jump in, I'm just going to define a few other things on the bottom of the board here that are going to be useful as we go through. So one of the quantities, all right. One of the quantities that we talked about yesterday was the flame aspect ratio beta, which is LF over R. And so this is just a non-dimensional way of talking about the, basically either your flame speed versus your flow velocity, right? The time average, shape of the flame, or that flame aspect ratio. Another non-dimensional quantity that they varied in this study that is just so insightful, they called capital K. So this is not little case k, which is the wave number. This is capital K, and this is equal to U naught over UC. And so if you remember yesterday, I made a big friggin' deal over the solution to the equation for d zeta dt, which had both a homogeneous solution and a particular solution, where the homogeneous solution described the disturbance convecting along the flame that was created by that boundary condition, or your pipe cleaner being stuck to your straw. And the particular solution is the local flame response due to the fact that the flow is oscillating everywhere in the domain, right? So we had these two disturbances, and this ratio describes the ratio of the convective velocities of those two disturbances along the flame. And so U naught is the convective velocity of the local disturbance. So this is the, the fact that the flow is fluctuating everywhere, and that, we said that U is equal to U bar plus some U prime, or here they use epsilon times cosine omega t. And so that's that epsilon-sized oscillation convex along the domain downstream with a velocity U naught. That root wave, that base wave, that homogeneous solution convex along the flame at some convection velocity U sub c. So this is the convective velocity of the base wave, or the non-local disturbance. And this is wildly important. If we have these two disturbances that are convecting at the same speed, they're always going to be reinforcing each other, because the first time they sort of affect the flame is at the base, and they all move downstream together. But if you have two disturbances that have different convection speeds, you're going to get interference phenomena. It's just facts of life. That's what happens. And so this parameter K basically tunes that interference. Okay, so questions on K? This is like, we're going to be looking at variations in K a lot. All right, cool. All right, so they define Struve-Hall number, because a bunch of the plots I'm going to show are Struve-Hall number as omega naught LF over U naught. So omega naught is the frequency at which the flow is being oscillated, flame length, which is up there, and then flow velocity. They come up with this quantity, alpha, which if you do the math, it just basically takes a term that's really gross and turns it into one value. So this quantity b squared, or beta squared over beta squared plus 1 shows up in a bunch of places. And I think Princeton, who is a brilliant but somewhat impatient individual, just said, can we turn this into one thing? And then alpha was born. This is important, however, because the other thing that falls out of this, they define something called eta, which is K times alpha. So this is your ratio times some effective flame shape. And so if eta is equal to 1, then UC is equal to U naught. If eta is greater than 1, then UC is less than U naught. And if eta is less than 1, then UC is greater than U naught. Did I do that right? Yeah, I did. Okay, cool. So it's really, the plots they put together are in terms of eta, not in terms of K. But basically, for a given flame shape, it tells you what's going on with K, which is what they did. And finally, it doesn't matter. Again, it just falls out of the math. They defined a second Struve-Hall number 2, which is just Struve-Hall over alpha. Just a shape effect, doesn't really matter. Okay, cool. The big deal here, though, is this guy, or this eta parameter that we'll see in a second. Okay, cool. So let's look at some results. So they went through, they did the math to look at the time variation of zeta here, and then actually they put it in the frequency domain, and then they solved for the dynamics of zeta at a whole bunch of different frequencies, or Struhel numbers, and played around with some of these other parameters, particularly k, in order to see what would happen to the response of the flame. And so the response here is defined as the normalized area fluctuation, A prime over A base. So they integrate all the fluctuations, they get a flame area. And so that flame area fluctuation over the time average flame area is their response. Okay, they give the response, I'm running out of room here, that's okay. In terms of this quantity G, which the reason I picked G before is because we're going to see it again. This is essentially the transfer function. So G is a function of frequency. And when you do the math, which I'm not going to go through, but you are very highly encouraged to read this paper because they do a nice job stepping through the math pretty clearly. There's two components. There's G of the base wave plus G local. And like I said, when you solve for zeta, you end up with those two parts of the solution. You can similarly then get the area fluctuation contributions from these two different disturbances, and that's what they play around with in the study. So the base wave contribution and the local contribution. Okay, so let's look at some results now that I've really talked this up. So this plot on the left, G local, they're calling G flow, and G base, they're calling G boundary condition. And this is the ratio of the response amplitude to the flow versus the response amplitude to the base, right? So these two different disturbances, as a function of Struhel number, how do they compare? The first one I want you to look at is this dot dash. It's 0.99 because if it equals 1, you get some divide by 0 jazz going on, and that throws off your solution. So let's say this is eta approaches 1, and you can see that if the convection velocity of these two disturbances are the same, then the area contribution of both as a function of frequency is the same. Their ratio is just 1. However, if you have either UC less than U naught or UC greater than U naught, you have these interesting phenomena where, in particular, you start to get these oscillations around 1 at higher frequencies. Right? Note that this is a log scale, and so these are much bigger differences than these are down here. But you start to see interference between these two oscillations as a result. I think the much clearer way, and here's the phase. Again, actually the phase is really important, so let's talk through the phase. So eta equals 0.99, so 1-ish. The phase is basically constant across the board because they're moving at the same speed down the flame, and so regardless of the forcing frequency, they're always going to be acting together. But then, as you change this, and the more that you change these two velocities relative to each other, you have bigger and bigger phase differences, and as you increase the frequency, those phase differences get bigger. Okay. This is the big one. So this is the conical flame, which isn't super exciting. What I really want to focus on is the wedge flame. So this is your pipe cleaner. And what this is showing is this is now that transfer function amplitude. This is both contributions together as a function of Struhal number. And you can see as you go towards 0, it goes to 1. So that's what transfer functions are supposed to do. Now, because we've got everything normalized, we don't have a divide by 0 problem anymore. So if you look at this eta, you can see it just goes up. But if you look at every other case, you get these really nifty nodes and antinodes in the transfer function, just like we saw in the measurements. So what's going on here? So now we need to go back to our pipe cleaners here. So if we just had the root wave, right? And let's say this oscillation is the root wave. This is going, at some frequency, is going to cause an area disturbance that convects downstream along the flame. However, if you now have the same disturbance, wait, let me try something. Okay. If you have the same disturbance and it's moving at the same velocity, then these guys are always going to line up, and so they will constructively interfere with each other. If you have this, let's say one of them is moving faster, you'll have points where, let's say, let's do this in the reference frame of one of these, points where they're lined up, but then you're also going to have points, let's say this one's moving faster, there will be periods in time where these now destructively interfere, right? Because this guy's moving faster than this guy. And then they constructively interfere again, and then they destructively interfere, right? And so two waves that are traveling at different velocities will, over time, cancel each other out. This doesn't go on forever, though, right? In this, let's say this wavelength, so this is a particular Struhal number, you only have 2 wrinkles along the pipe cleaner here, and so there's only a finite amount of space for these to constructively and destructively interfere. And so depending on the difference between the velocities, you can kind of run out of space. And so maybe as you integrate over that convection period, it only kind of cancels out, but not totally. But then if this guy moves a little bit faster, it will completely cancel out. But then remember, phase is a circle, so if it just keeps moving faster, it'll only kind of cancel out again. And so this is where this periodic constructive, destructive, constructive, destructive, constructive, destructive comes from. And you can see that the periodicity of this depends on that difference in convective velocity. So you don't have this super simple flame. This is laminar. You have one input disturbance. It results on 2 disturbances on the flame. And you still get an interference pattern because of the boundary condition and the resulting flame kinematics. The other thing to note is that there's an envelope to this. That really beautiful envelope is the low-pass filter of the flame. Okay, we are at 3 o'clock, so, and this works out well. This is a good time. Well, no, I'm going to show you one more slide, and then we'll take our break. This gets worse as your forcing amplitude gets higher. So this is now Struhal number, same amplitude, same wedge flame. For a constant eta, so this is eta of 2, so your base wave convection velocity is less than your local wave convection velocity, but now we're really amping up the amplitude of the initial input. So eta is u prime over u, so the incoming fluctuation. In the linear limit, which they did analytically using an asymptotic expansion, you get very clear response. But as you increase the amplitude, you're basically creating more and more severe wrinkles that then, you know, they kinematically restore themselves faster and faster. And so these effects, this convection time that you need to see that interference, this constructive and destructive interference, becomes too long before these really severe flame wrinkles destroy and annihilate themselves. And so at some point, you don't even see the interference anymore. All you see is the low-pass filter behavior of the flame because you've created such significant cusps that they burn out faster than the interference can happen as the disturbances move along the flame. Okay, so as we go into coffee, key point, nodes and antinodes in your flame transfer function tell you something about the interference of multiple disturbances. And the sources of those multiple disturbances in a simple flame like this are the base wave and the local. But when you get to more complex flames, which is what we'll look at when we get back, you can have even more disturbances that complicate the picture more. All right, I couldn't have timed this any better. So let's take a 15-minute break, and then we'll come back and we'll look at some data and some pretty neat measurements that were made to look at this effect more significantly.